All right, so hello, we're going to do 7.6 and 7.7 today. These are going to be all about just doing differential equations with separation of variables. We see 7.6 is finding general solutions. With 7.7, we're going to find the particular solutions. So these two are pretty much the same thing, just one kind of goes a little bit further than the other one. So the first thing we got to do is actually talk about separation of variables. And to separate variables, all we want to do is say we want the y's on one side and then the x's on the other side. So that's going to be our goal. We're going to try and get the y's on one side, the x's on the other side. We've done stuff like this before. But for the first one, we see we have this x squared. We want to get rid of that, put it on the other side. So we have to do minus x squared on both sides. So that gives us 3y dy dx equals negative x squared. Now we have to realize that in Leibniz notation, this is an x. So this is still on the wrong side. We got to move that dx to the other side. So since we're dividing by dx in Leibniz, we have to then multiply both sides by dx. So our final answer is actually going to be 3y dy equals negative x squared dx. Because that dx and that dx will cancel out. So that gives us negative x squared dx. So we see we've got the y's on one side, all the x's are on the other side, so our variables have been separated. So for the next one, we got sine x y prime equals cosine of x. This is supposed to be sine of x in parentheses, so I'm going to put my little parentheses there. So again, we see we want to get the x's away from the left side. So it looks like we're just going to divide both sides by sine of x. So we get y prime equals cosine of x over sine of x. Now this looks a little bit different than this one, because this one had the dx over here at the end. We saw we had to do that step, so it might seem a little bit strange. It seems like we should have to do that, and we do. The problem is y prime is actually hiding a dx, because y prime we can also rewrite as dy dx. So the dx is actually hiding, even though it doesn't show up there, it's hiding. Cosine divided by sine, that's cotangent. So last step, just like we did before, we're going to multiply both sides by dx. And so the final result is going to just be regular dy equals cotangent, not cosine, cotangent of x dx. So you can double check. You always want to have a dy and a dx on two different sides. That's how you kind of know that everything's been separated. For the last one here, we've got x y prime divided by e to the y plus 1 equals 2. Same deal. We're going to go ahead and say we need to get rid of this x. So we have to divide both sides by x. So we get y prime over e to the y plus 1 equals 2 divided by x. Same deal as before. We see we have y prime. We need to split that into dy dx. So we're going to say dy over e to the y plus 1. And instead of writing dx like below the dy, I'm going to say we split it up into kind of a fraction, dy dx. This is still just 2 over x. We can just leave that as 2 over x. If you want, you can make that x the negative 1. It's your choice. And then at the end, same deal. We need to multiply both sides by dx. So we multiply by dx on that side. On that side, we get dy over e to the y plus 1 equals 2 over x dx. And so that's completely done. So we can see in every single case, the dy's are on one side with all the y, and then the dx's are on the other side with all the x's. So that's how we know we've fully separated our equation. So that's just the first part, which is to realize, oh, separation of variables is splitting up the y's with the x's. Now the whole goal is, now we see we got dy, we got dx, we kind of know what we can do on both sides. That's what we have to do when we find our general solution, is to take that last extra step. So to find the general solution, again, we want to use separation of variables because we see we've got x's and y's. So you might think, I'm not sure which section I want to put the y's on. It looks like it'd be easier to move the x's over to this side. But the thing that's in charge is the dy dx, because that's the one that always has to be on top. So this tells me automatically I have to multiply both sides by dx. So that gives me x squared plus 4 dy equals xy dx. Now I don't really have much of a choice. Since the dx is on the right, all the x's have to go on the right. Since the dy is on the left, all the y's have to go on the left. So I don't get a choice. I have to follow the rules from the dy and the dx. Well, that's okay. So put the x's on that side, so the x's have to go away from here. So we got to divide both by x squared plus 4. The y has to go away. So to make the y go away, I have to divide both sides by y. And again, this is to get all the y's on one side, and we're trying to get the x's on the other side. So after we do this, we're going to end up with dy over y, because that's what we got left on the left side. And on the right side, we've got x dx over x squared plus 4. So now we have to think, all right, we got a dx on one side. We need to get a general solution. How do we get rid of dx? So to get rid of dx, we got to do what we did in the last chapter. We got to integrate. So we're going to integrate both sides. Now the cool thing is, this only has y's, so everything is correct. We don't need to do any sort of crazy implicit integration or anything like that. That's all good. Same deal over here. This only has x's. There's no real tricks to it. It's just the same stuff that we did last time. So if we have dy over y, unfortunately you'll see these show up a lot. This is going to be like a 1 over y. So this is going to be the ln of y, absolute value, plus c. Again, we need to have the c because I don't have any limits of integration. On the other side, that one looks a little bit trickier because we got x over x squared plus 4. So it looks like it might be one of those trig ones. Might also just be a regular ln. So let's split it up. Let's say u is going to be x squared plus 4. So du equals 2x dx. All right, so if I wanted to make that look a little bit nicer, we could say that's the integral of 1/2 2x dx over x squared plus 4, which is going to be the same thing as the integral 1/2 the integral. This is all du. This is all u. And if we have du over u, just like we had dy over y, we're just going to end up with ln of u plus c. So that one's a little bit tricky to do the integral. It does look like it might be one of the trig ones, but it's not one of the trig ones. It's just a regular ln. And in this section, they love to do ln's. You're going to see a lot of ln's. You're going to have to divide to get things onto the other side. So we need to then find out our final equation. So we know we got to substitute back in for u. We said u was x squared plus 4. So let's go ahead and substitute that back in. X squared plus 4. And I also pulled one other trick. So I had 2 c's, but if I subtract c from both sides, it's still a constant. It's not 0. It could be 0. It doesn't have to be 0. But sometimes they like to say this is c1 and c2, and we just get a final c at the end here. They even call this c3. So if you want, you can use all the little subscripts. If you just know that it's just constants and constants and constants, you don't need the little subscripts. All right, so that looks pretty decent, but we want a general solution. So that means we want to try and get y by itself. So let's try and go ahead and get y by itself. So in order to get rid of the ln, we know the opposite of ln is we got to do e to both sides. So we're going to do e to both sides. So that's going to give us y, well, absolute value of y. So that's a good thing. At least that's good. And then we have, this is not really the most positive thing we have, e to the 1/2 ln x squared plus 4 plus c. Well, that looks pretty complicated. So let's see how we can simplify that a little bit. Well, we know from the ln rules, from all the log rules, we could write this as e to the ln of the square root of x squared plus 4, because we can make this 1/2 into an exponent. Still plus c, this is all in the e. Then we also know from our exponent rules, this is the same thing as saying this is e to the ln square root of x squared plus 4 plus e to the c. I guess I should keep saying c3. Keep my subscripts. Not plus, multiply, because when we're adding the exponents, we're multiplying the same base. So we have to use our exponent rules in addition to all of our log rules. So you might think, all right, looks like we're almost done. We're almost done. On this side, we still have the absolute value of y. So now this really simplifies things, because we get square root of x squared plus 4, because ln and e cancel each other out. E to some constant is just another constant, so we can call this c4 if we want. So we just have a new constant. I don't like this absolute value, so I'm going to say y is going to be plus or minus c4 square root of x squared plus 4. Again, if you don't want the subscript there, you can say that's just c square root of x squared plus 4. And so that gives us our whole final equation. We have an equation in terms of y. It's not really super friendly, but it's what they wanted. We used our calculus to get there. So if we go all the way back up here, wow, that was a long problem, but we did find our general solution. That's our general solution. So if we graph those, or if we graph this, we should get a slope of essentially this divided by, or xy divided by x squared plus 4. So that's our general solution. So that's the end of 7.6. So I'm going to stop it for right now. I'm going to put these together. That's 7.6. All right, we're going to put them together. So now they're together. This is 7.7. So 7.7 is going to be particular solutions. So it's going to be what we just did with more steps afterwards. So as long as we know what we did before, we can see what our new steps are going to be. So for our particular solutions, the whole idea is that we're going to have some initial conditions to plug in. So once we get our answer, we're going to have to do some more plugging in and doing some more algebra. So typically, if you have to get the initial conditions, this is what they'll tell you. Either they'll give you a coordinate point. This is x, this is y, just like normal. They'll tell you something like f of 4 equals 10. Well, x is 4, y is 10 in that case. They'll just straight up state x equals 7, y equals -3. So they'll just tell you what the numbers are. Or they might give you a situation. This is usually the trickiest one to do. So for example, if a car is at mile marker 5 after 20 seconds, then you have to realize that this is going to be probably your distance, and this is going to be your time. So those will probably be the variables that they use. It'll be like one of the physics ones that we did. So that'll be the trickiest one to do, is to realize you have to interpret from a situation. So how do we do it? Well, we kind of do it the same way we just did 5.6. We have an initial condition. Find the particular solution of the equation. We basically ignore this until we get to kind of a good point where we can plug them in. So we're going to use our separation of variables. X is on one side, y is on the other. In this case, we do have a choice because the dx and dy aren't above each other. I think I'm just going to move this dx. Is that going to look easier? Maybe. So I'm going to subtract xy dx from both sides. So we get e to the -x squared. Yeah, all right, I think that's going to look nice. Dy equals -xy dx. All right, well, just like we did before, x is on one side, y is on the other, right? So we're going to have to divide by e to the -x squared. Okay, we can do that though. On this side, we got to divide by y, because we don't want the y over there. So the y's are going to cancel, and then this e to the -x squared is going to cancel. All right, so it looks like that looks pretty solid. Looks like we got y's and x's are now going to be separated when we simplify. So this is y squared minus 1 over y dy. This is -x over e to the -x squared dx. All right, I'm not really liking how either of those look, so let's see if we can use a little bit of algebra to simplify before we take the integral, because that would be the next step, would be to take the integral. Well, on this one, I guess we could divide both of these by y. So we can say this is going to be y dy minus 1 over y dy. All right, those both look friendly. Those both look like they're going to be pretty good to integrate. I'm happy with that. On the other side, e to the negative x squared means we can actually flip that to the top, right? We can make this negative x e to the regular x squared. Well, that's better. It's getting better. Like I said, I'm totally happy with the y's, so I think right now I'm going to go ahead and integrate that side, because we might as well. With these, I think I'm probably going to need to do a u substitution. I'm probably going to need to say u is going to be x squared, so du is 2x. All right, 2x dx, which means that I've got a negative x dx over here. So if we're doing it the other way we did it, we could say du over 2 equals x dx. So I need a negative 1/2. All right, so that looks like that's what I'm going to have to replace that with. So negative 1/2 du. So I replace the negative x dx with a negative du over 2. I guess I didn't need to replace the negative sign with a negative sign, but I did. And then this x squared is going to become a u. So e to the u. All right, that looks like that's going to be reasonable to integrate, but let's take care of this side first. Integral of y is y squared over 2 plus c. Integral of 1 over y is ln of y. Oops, that's a minus sign. Ln of y plus c. I guess we want to move those up a little bit. There we go. All right, so that side looks like it's pretty good. I'm going to keep that side in green for a little bit longer. So 1/2 y squared minus ln of y. And again, I'm just going to say, I got plus c minus c is just going to be some other c. So I'm just going to leave them as c. On this side, we have to integrate now. So the integral of e to the u, integral sign right there, that looks like the best place for it. Integral of e to the u is e to the u. So that's great. Plus c. So now I got to replace back for u. So negative 1/2 over like that. E to the u. So e to the x squared. Well, negative 1/2 of c is just going to be c. And I can even subtract this c and just lump them all into one giant c. So that's going to be what I've got. Now, last time we said we had to get y by itself. I don't think it's going to be prudent to get y by itself here. That seems like a hassle. One thing that might make things a little bit nicer is if we multiplied everything by 2 before we plug everything in. So y squared minus 2 ln y equals negative e to the x squared plus c. So that looks like I'm pretty happy. Could be above here, could be this one. But now I see when y of 0 equals 1. So I got to use my initial conditions. So my initial conditions were y of 0 was 1. Okay, well, my initial conditions tell me that I need to plug 0 in for x and 1 in for y. 2 ln of 1 equals negative e to the 0 squared plus c. All right, well, 1 squared is 1. Ln of 0, or ln of 1 is 0, so 1 minus 0. Well, let's say 2 times 0. Equals, well, e to the 0 is 1. Or sorry, e to the 0 is just e to the 1, so that's just e plus c. So if I do this, I get 1 equals negative e plus c. So I can add e to both sides. I get 1 plus e equals c. All right, well, looks like that's what we got. So since I know what c is now, what I get to do is I get to go all the way back up here and say, all right, I guess I want my final answer to be y squared minus 2 ln of y equals negative e to the x squared plus 1 plus e. And that's going to be what my final result can look like. So that can be my ending point. So again, it's a lot of what we did with the last section, but now we got the one extra step of we have to plug in our initial conditions. All right, let's fix this up real quick. I caught this before I uploaded everything. E to the zero is e to the 0. So this should not be an e. This should be a 1. So we should add a 1 here on both sides. So c should be 2. So let's go ahead and make that little quick correction, just so we're good with that one. There we go. That's not a very good 2. I want to make that get better. There we go. So yeah, that's about it. So yeah, I just made a quick little mistake. That's okay, but that's that's something that we catch in class, and that's okay. It's okay to make mistakes. It's always good to double check your work. All right, so let's move on then. So last one I want to check out is one more example with the whole shebang. We want to find the equation of a curve that passes through 1, 3, has a slope of y over x squared. So we have to interpret this from the situation. It says since we have a slope of y squared over x, that means that dy dx, which is the slope, is y over x squared. All right, seems pretty good. We're going to do like we just did. We need to make sure we get dx on both sides. So we're going to multiply both sides by dx. So this is going to give us dy equals y dx over x squared. So the first thing I want to do is I could have done this all in one step, but I wanted to just show, hey, the y's have to go over on the left, the x's have to go over on the right, because now we can divide both sides by y. And so this will give us our equation that we want to work with, which is going to be 1 over y dy equals 1 over x squared dx. All right, looks like we're ready to integrate from here. So let's see. Can we do it? We can do 1 over y. That doesn't seem too bad. 1 over x, that might be a little bit more difficult. So this is just ln of y plus c. But we got 1 over x squared dx. Well, let's think about this one. So we can't use an ln because that's not just 1 over x. So 1 over x squared is x to the negative 2. Oh, but we can use the power rule. So let's see if we add 1 and then divide by that number. So we get x to the negative 1 over negative 1. So that's negative 1 over x. If we do take the derivative of that, yeah, negative 1 becomes negative 2. Okay, yeah, that makes sense. Okay. So we can solve this one using the power rule. So we're going to integrate that one using the power rule. So we get negative 1 over x plus c. All right, that actually turned out to be pretty good. That was not as bad of an integral as the last one was. Just like we did before, we're going to just lump the c's all together. So ln of y equals negative 1 over x plus c. Now, we can choose, if we want, we can take e to both sides. I don't know if that's going to be a good choice right now. Or we can just go ahead and substitute. Since we have to find a particular solution, we're finding the equation of the curve, we got to find the particular solution. We may as well just plug them in right now, and then we'll mess with all the stuff later. So the initial condition we're given is it passes through the point 1, 3. So we're going to have to plug in 1, 3 into this. It's going to pass through 1, 3. So that means x is going to be 1 and y is going to be 3. So we get ln of 3 equals negative 1 over 1 plus c. So ln of 3 equals negative 1 plus c, or ln of 3 plus 1 equals c. Okay, again, that looks like a kind of an odd choice for C, but we saw in the last one, yeah, sometimes we get some weird stuff. We'll see if it works out. So I'll probably double check it again after I put it up, but that's what I got for C. So we're gonna plug that in for C. So we get ln of y equals negative 1 over x plus ln of 3 plus 1. Now, I'm quite content with that. That is an equation. If it was multiple choice, and again, there's no multiple choice in the test this year, but we do want to talk about this because we want to see some other forms of how it might look. We could get the y by itself, so we could take e to both sides. So if we did that, that would be quite complicated, I think, but we'll try it out. So we get e to the ln of the absolute value of y equals e to the negative 1 over x plus ln of 3 plus 1. Okay, that doesn't look promising, but let's see. Maybe it'll get a little bit nicer. E and ln cancel. We can rewrite this one the same way we did the other one. E to the 1 over x times e to the ln of 3 times e to the 1. Well, actually, that turns out really nice. E and ln cancel. This is just e. So this is actually 3e e to the negative 1 over x. All right, well, I guess y is going to be plus or minus 3e times e to the negative 1 over x. Okay, that actually turned out to be pretty nice. Turned out to be pretty decent. Now, one thing we can notice is this is always going to be positive because e to something is always going to be a positive number. E is always a positive number. 3 is always a positive number. And since we did an ln, we probably want that to be positive. So I don't know if we're going to need the plus minus. We might just want the plus version. But I'm pretty happy with reporting that answer. That looks like it's going to be pretty nice and succinct. And I believe that's everything for this section.